Hey guys, in this video, I wanted to cover apparent weight, what it is, and how to solve problems with it. Let's start off by talking about what apparent weight is. Apparent weight is just simply what you feel like you weigh. So let's just say you weigh 1,000 newtons. That's your actual weight, okay? Your weight, again, is your mass times gravity, okay? So let's say you're traveling in a car. Let's say you go over a speed bump. When you go over that speed bump, you're momentarily going to feel lighter, okay? You're going to come off the seat just a little bit, and you're going to momentarily feel lighter. It's that feeling of being a little lighter that we're trying to calculate, okay? So we're trying to find out, hey, how much lighter are we, okay? Again, it doesn't mean that we lost weight. It just means that we're feeling like we're losing weight. Now, this can happen in many scenarios, like when you're on a roller coaster, right? You feel heavier at some points. You feel super light at some points, right? That's the thrill of riding a roller coaster. Same thing with elevators, which is why I made this a part of the elevator unit. A lot of times, elevator questions are going to ask questions that involve your apparent weight and finding your apparent weight, if it's going up or if it's going down. So again, just to clarify, your apparent weight is just how much the ground pushes back up on you, or whatever the surface is. So if you're sitting in a car, like I said, it's the amount of force that's pushing back up on you. And if you're going over a bump and you're momentarily coming slightly off the seat, then the seat isn't pushing as hard on you as it normally would, and so you're going to feel lighter. Okay, so that's what causes apparent weight. It's the feeling of the surface not pushing back up on you as hard as it would normally than if you were just standing like on a level ground. As you can see here, I've actually drawn some visual representations using FBDs, of course, and in the first diagram, you can see that the normal force and mg, or your weight, are the exact same. And so what this means is that you're going to feel exactly what you weigh. However, in the second diagram, you see your normal force is much greater than mg. And so what that means is that you're going to feel much heavier than you weigh, okay? Because, again, the surface is pushing up harder on you than you are pushing down on it. So, in other words, you're going to had that feeling of heaviness. Again, does that mean your weight changed? No, your weight's still mg, but you're feeling like you're a lot heavier. Same thing in number 3, right? In this case, you're actually feeling a lot less heavier because your normal force is less than mg. Okay, so that's a quick explanation on what apparent weight is. Now let's go ahead and actually do a problem and solve for apparent weight. All right, in this problem, you're standing in an elevator that's traveling upwards and decelerating at a rate of 3.1 meters per second squared. What is your apparent weight given that on the ground you weigh 755 newtons? So let's go ahead and actually break this down into two FBDs. The first one I'm going to draw is the one where he's just standing on the ground. So mg, and then his normal force is going to be equal and opposite. Okay, again, this is on the ground. Now in the elevator, it's going to be slightly different. I'm going to start off by drawing the dot to represent the person. I'm going to draw a downwards arrow to represent the weight. And remember, that weight is going to be identical in the elevator and on the ground. What's changing, however, is the normal force, okay? So the normal force is going to be what's pushing back up on you. And so if the normal force is less, it's going to feel like that person is going to weigh less. And if it's more than mg, then it's going to feel like the person is heavier than what they actually weigh. And so in this problem, it says that we are traveling upwards and decelerating at a rate of 3.1. So a deceleration means that we're going to be, and again, if we're traveling upwards, a deceleration would imply that acceleration is in the opposite direction. So that means acceleration must point down. And the only way for acceleration to point down is if we have a net force down. So in other words, we need to draw the normal force smaller than mg, okay? And so again, when normal force is smaller than mg, we got a net force down, and therefore an acceleration that's downwards, which is opposite to velocity, which is going up, and so therefore we have a deceleration. From here, it's very simple. We just continue following the force problem-solving framework that we've been using in the past, and we sum up forces. So again, F net in the y direction is equal to may, and the two vectors in the y direction are mg and n, and I like setting the bigger vector as the positive direction. So mg is positive in this case, normal force is pointing in the negative direction. So it's going to be mg plus negative n, or I can just put minus n, is equal to ma in the y direction. Alrighty, from here we need to actually solve for the apparent weight. Again, the apparent weight is really just the normal force. It's what we feel like we weigh. And in this case, we should get a smaller number than our actual weight. So let's go and solve for n. N is equal to mg minus MAY. We can actually simplify, so we can do that by factoring out the mass. So G minus AY. Okay, and from here we can actually just go and plug in the numbers directly into the calculator. We know the acceleration, we know gravity, we even technically know the mass, although they don't directly give that to us. However, remember that they give us the weight. And if the weight is 755, right? If mg is equal to 755, and in this case we're going to use gravity as 9.81, and that means the mass is simply going to be 755 divided by 9.81. So again, technically they did give us the mass. And again, mass does not change. Mass is a constant no matter where you are. If you're in outer space, if you're in an elevator, if you're on a different planet, your mass is what you're made up of, and it doesn't change. Your weight is what changes with gravity, okay? Anyway, so this is your mass. We can plug that in. And I got an answer of about 516.4 newtons. And again, just to confirm with the diagram that I had earlier, the normal force should be smaller than mg. The normal force in this case is 516. The weight was 755, and so that indeed is smaller than the weight. So in other words, it means that we're going to be feeling a lot lighter on this elevator as we decelerate downwards. And you can even put yourself in the situation, maybe the next time you're in an elevator, as soon as you start dropping down or speeding up downwards, you'll feel like you're momentarily lighter, right? You're momentarily lifting off the ground. Again, it doesn't mean that you actually lost weight, it's just feeling like you lose weight. All right, that's it for this video. Hopefully this was helpful, and hopefully this cleared up a lot of the misconceptions about apparent weight. It can be quite confusing, so there are more problems that you can work on to help you fully solidify this concept. All right, take care, and I'll see you in the next video.